Okay, we need to start chapter 9, which is a chapter on bonding theory. And we're going to start out, and actually spend quite a bit of the time of this chapter, talking about something called Vesper Theory. I'm fully aware that that does not actually spell the word Vesper, but most chemists pronounce it that way. This is an abbreviation for something that stands for valence shell electron pair repulsion theory, which is why we abbreviate it. Okay, so the idea is actually not that complicated. So when we have Lewis structures, like we did in the last chapter, and Lewis structures are like the first step of what we're going to be doing here, so we need to be good at Lewis structures. But we say, we draw bonds for lines, or lines for bonds, we draw dots for the electrons that are lone pairs, but the idea is, and we say that they're paired, but the idea is that electrons still repel each other. It's the repulsion part. So whether they're lone pairs or shared pairs, whether they're bonds, the idea is that those electrons on the outside that are part of the bonds, all the valence electrons, are the ones that are repelling each other, and it's forcing the atoms to get as far apart as possible. The result is that basically electrons repel, and that creates geometries. Let's go with 3D geometries. So most of this topic is the idea of what is the three-dimensional shape of molecules. When we did Lewis structures, we drew everything as 90 degrees, and we kind of ignored this concern. And I'm fine with you doing that for Lewis structures, but now we need to deal with the concept. So the first thing we need to do is define what counts as something called an electron group. Some textbooks call it different things. I am going to be posting a copy of this table for you guys to print out and use on exams, and they refer to it as electron groups, so that's what we're going to do. So an electron group counts as single bonds, double bonds, triple bonds, and lone pairs. And the idea is each of these count as one group. So I'm fully aware that triple bonds have 6 electrons and single bonds only have 1. We count it as one group. Okay. And there are different types of geometries that we can get out of this. The first is called electron group geometry, and it's actually the easiest of the bunch. Okay. Electron group geometry does not distinguish between any of these, and we only care about what is connected to the central atom. So if you have multiple central atoms, you won't have a geometry for the molecule, you have a geometry for each central atom. But if we don't distinguish between single bonds, double bonds, triple bonds, and lone pairs, this is pretty easy. So basically, number of groups, and then you get a geometry that corresponds with it. And this is the foundation of the more detailed version where we do start distinguishing between things. So if you have a central atom, this is also, I guess I should probably point this out too. This uses the AEX system. Okay, some books use different letters, but A is the central atom. E is an electron group, so basically just a lone pair. And X is pretty much anything bonded. So a bonded atom. So a terminal atom connected to it. Okay. So if you only have 2 groups, you have a central atom, there's only 2 things attached. The idea is that these things repel each other and they want to get as far apart as possible. Well, if you only have 2 groups, the farthest they can get apart is linear. They can basically form a straight line. I guess I probably should draw pictures of these things. So let's say they're both bonded atoms. But the idea is the farthest they can get apart is 180 degrees. Okay, that's the bond angle. We'll deal with bond angles in more detail as we go through this. Okay, if you have 3 groups, the idea is that, I guess I'll draw it first. the most you can spread them out is like that, where they're 120 degrees apart. I'm going to be labeling all these as X's, none of them are going to be E's, because we're not distinguishing between them in this. Okay, but the bond angles are all 120 degrees. You'll note that the more things you shove in there, the closer they're going to be together, so the bond angle goes down. But this is as spread out as we can get them. This has a weird name, that's okay. This is called trigonal. Help if I spell things correctly, sorry. Trigonal planar. So the idea is trigonal means three-sided, and planar means it's all flat, so they're all in one plane. Okay? If you have 4 groups, at first, especially if you draw a Lewis structure, you draw everything 90 degrees apart, and it almost looks on trend. Everything's decreasing as we go. But it turns out that we have 3 dimensions to work with, so we can actually get more than 90 degrees in there. So what we end up with is something that's going to require a new visualization of how to draw things. So we're going to have this going straight up. This is going to be off at kind of a weird angle. And this is going to be a wedge, and this is going to be a dash. The wedge means so the ones that are flat, the straight lines, are in the plane of the paper. The wedge, which I guess I should label a little better, means towards you. Red pen kind of sucks, sorry. And dashes means away from you. Okay, so the idea is this one's straight up, this one is down at not quite 120 degrees. These ones are at the same angle, but they're not in the plane of the paper. This is pointing towards you and this is pointing back. And the bond angle for this actually comes out to be 109.5. Okay. This is called a tetrahedral. Okay, it is a really, really common geometry. I have models of some of these. I thought I had a tetrahedral made, but I can make one real fast. 3-dimensional geometries. This is dopamine. Anytime you've ever felt happiness, this is what the structure looks like. But you'll notice none of this stuff, most of this stuff isn't flat, okay? You're getting like weird angles we gotta account for. So I'm gonna rip this apart so you guys can kind of see what it looks like. Sure, this will be easy. Okay, so this is what a tetrahedral looks like. So if we were trying to orient it with this paper, the idea is these two would be in a flat plane, in the same plane as the central atom. This one would be facing towards you, this would be the wedge, and this would be the dash. It's kind of pointing back. So this is what we're trying to represent with this. Okay, but it is 3-dimensional. There isn't like one side where it's facing up and one side where it's facing down. No matter how you rotate it, it's the symmetrical all around. Okay, so this one comes up a lot, especially if you take organic chemistry. This is like the default answer for everything. Okay. So continuing our table, we need to look at number of groups and then the geometry that goes with it. If you have 5 groups, these are things that violate the octet rule because you can't have more than 4, because each bond has 2 electrons. You can't have more than 4 bonds and have an octet. But we learned in the last chapter that sulfur, phosphorus, chlorine, things in the 3rd row or below can have more than an octet, so this is not uncommon. This one is called a, brain is shutting off here, a trigonal bipyramidal. And I actually have one made. So, I'm trying to show you the best way to do it. So what we have is it's essentially a linear and a trigonal planar at the same time. So these 3 are in the same plane as this, and they are 120 degrees apart, as far as you can get them. And then perpendicular to all of that, you have these 2. So what we find is that this bond angle is 90, this one is 120. This one's the complicated one of the bunch. Still pretty common, but it's the complicated one. So I'm gonna define or draw a few things here and try to label stuff as best I can. actually going to switch colors on this. So if we tried to draw it with the wedge and dash thing, we could actually get 3 of these in one plane. So these 3 are in one plane, but also these 3 are in one plane. So you can visualize the blue ones as being like a trigonal planar, and then perpendicular to that is a linear. Okay. As far as bond angles, these are all perpendicular, so they're 90. These ones in the plane, in this plane, are 120 degrees. This is the weird one in the bunch. They also have different terms for the positions. So like the tetrahedral, they're all equivalent. It doesn't really matter where you put them, but this one it does. Okay. I'm running out of colors here. Okay. The ones at the top and the bottom are the axial positions. If you visualize this as the axis, you could visualize this rotating and these are all in one plane. If this is the axis and these are all rotating, this would be the equator. So the blue ones are the equatorial. Okay, this one has a lot of detail. It's kind of the messy one of the bunch. Okay. Okay. The next amount of groups that you can have on there is 6, and this is the absolute maximum. You cannot physically have a molecule that has more than 6 groups attached. This one is essentially, you could visualize it as an extension of this. There's an up and a down, and then in the plane that normally had the equatorial ones, we have to fit 4 things, so technically everything's 90 degrees apart. So this one, everything is symmetrical, actually. This one's actually easier despite having more things. So in terms of drawing it, it tends to look like this. And everything is 90 degrees apart. Everything is, kind of do it like that, I guess. Basically, everything's 90 degrees apart, okay? Makes it easier to visualize, okay? So this one, we have like a top and a bottom, and then we have stuff that's in the middle. This one, it doesn't really matter, okay? You can have a top and a bottom and stuff, top and bottom and stuff in the middle, but you can also flip it, and it's the equivalent answer. Okay, doesn't really matter. Okay, the confusing bit on this one is the name. So when we had a tetrahedral, this was called a tetrahedral because if you connected these 3 triangles, you get a side. This is one side, this is one side. You end up with 4 sides. It's like a 4-sided diamond thing, pyramid. Okay, that is called a tetrahedron, which is why this is a tetrahedral. So even though we have 6 things attached, we technically get 1, 2, 3, 4, 5, 6, 7, 8. We get 8 sides if you connect 3 at a time, which means this is called octahedral, despite only having 6. So the name does make sense if you understand how the shape that it forms, like the surfaces would form. I would have been happier if they had said hexahedral because 6 is hex and 8 is octa, but it is what it is. Okay. So we are going to learn more about how to do this stuff. Right now, we have not differentiated between lone pairs and bonded pairs. Okay. If you have everything the same, you don't differentiate, you get electron group geometries. In the next video, we're going to learn how to deal with molecular group geometries when we do start distinguishing between the lone pairs and the bonded pairs. Thanks.